Hello everyone, so today I'm gonna present our recent work, Neural Networks at the Interdomain Points. So let's get started. There are emerging probabilistic perspectives trying to explain neural networks. Neural network Gaussian process states that the infinite-wise neural networks at initialization are Gaussian process priors. And the serial neural tangent kernel explains the training dynamics of infinite-wise neural networks. So they have achieved great successes, for example, to explain the global convergence of neural networks. They rely heavily on the infinite-wise assumption and ignores the importance of individual weights. Empirically, it is observed that their performance fails to match neural networks with standard training procedure. In this work, we established a framework to explain neural networks using sparse Gaussian process. A sparse GP uses inducing points to approximate the true posterior of a GP, and the inducing points are a small number of inputs summarizing the training data. When we use more inducing points, we approximate the true posterior better. So what's the connection between a sparse GP and a neural network? Let's look at their formulations. The predictive mean of sparse GP can be written as a product of kzx with a vector, which is kzz inverse times mean. And the two-layer neural networks can be written as a product of the activation of the first layer outputs with the second layer weights. We actually observe a similar structure here. The left term is a nonlinear transformation of x, and the right term is linear coefficients. So imagine that we match the linear coefficients to be the same for both equations, and we let kzx equals sigma wx. Then both equations become exactly the same, and we match the sparse GP with the two-layer neural network. However, there's a problem. The problem is that activation sigma is not necessarily a positive step function, so it cannot be a kernel. Luckily, the interdomain in these points save us. An interdomain in this point is a function z mapping from the input space to the output space. And a variational Fourier features generalizes the kernel function so that it can be defined between an interdomain in this point and the input x. So that kzx equals z of x, and kzz prime is the RHS inner product between these two functions. Now, we can use the technique of variational Fourier features to connect a sparse GP to a two-layer neural network. We use I to indicate the index of the hidden unit, Zi being the ith interdomain point. It is defined as the S activation. Using the technique of VFF, the kernel function between Zi and X becomes exactly the ith activation, so that we match the left nonlinear transformation term exactly. If we use M equals kzz times A, then the right linear terms becomes exactly as well. So that finally, we can see the predictive mean of sparse GP becomes exactly the two-layer neural networks. And the width of the neural network is the number of inducing points in the sparse GP. When we use wider neural networks, we are expected to approximate the true posterior better. We have connected the two-layer neural network with the predictive mean of sparse GP. What we can use this for? We can extract uncertainty directly from a post-trained neural network. Firstly, we train a two-layer neural network by standard backpropagation, and this is only a deterministic neural network. After training, every hidden unit can be seen as an interdomain in its point in the sparse GP, so that we can directly compute the predictive variance of the corresponding sparse GP. We approximate it using the Nernst-Trom residual error. Let's look at some results. The left figure shows the predictions of two-layer neural networks using cosine activations. We can see it fits the data well, but provides no uncertainty. Using our framework, we cast every hidden unit as the interdomain in this point of the sparse GP, so that we directly generate predictive variances from the deterministic trained neural network. From the red figure, we can see it generates reasonable uncertainties. This current work is only preliminary. It opens up a lot of possibilities for future works. For example, how about multi-layer neural networks? How about convolutional and recurrent neural networks? And how does this framework help us to understand neural networks in terms of generalization and optimization? This is all the presentation. Thank you for listening.